Test one. So if you've been thinking about building a CNC machine for yourself, a couple of considerations you want to make. So I'd like to go through that today for this video and talk about some things that you should be thinking about when designing and building your own CNC machine. So for me, from the start, I knew that I wanted to build a machine that would cut steel, stainless steels, you know, sort of harder things, not just wood and bits and pieces like that. So I built this machine to be able to handle that kind of load, and that's why it's so big and beefy. Basically, the construction of the machine is all scrap steel. So realistically, the actual scrap steel in this machine has cost me absolutely nothing. All it's really cost me is time. So the boilerplate here, this is a 50mm thick piece of boilerplate, and that's my main sort of thing that I've mounted everything to. The spindle housing and everything was made again with scrap steel. This part here that actually holds the spindle, this was one solid piece around, and then there's another solid piece around in here, and then this is a pipe. Basically what I did was I rough turned the bore of this chunk, then I rough turned the bore of this, and then I welded all of that together, and then I sort of finished machined it all together, and then I welded the sides and everything on and made this part to hold all of the air ram and things. The Z-axis is a 200mm by 200mm by 10mm box section. Again, scrap offcut. And then that's all welded to some 15mm flat bars. Underneath the flat bars on the Z column, I've gone and used dry pack. So it's called Seeker 212, I believe. It's a dry pack that we would use. We actually use it because I'm a builder in my day job. We actually use it to pack steel portal frames and bits and pieces like that. So I sort of knew that it would be nice and strong, and it allowed me basically to be able to get everything lined up perfectly, so that I knew that this was going dead up and down this way and this way, which I tested that with an angle plate on the base of this, and then I run a dial indicator off of here, up the plate this way and up the plate this way. So after I'd done that, I went through and I dry packed underneath all of the column, and then I let it dry for, I think it was about 2 or 3 days, and then tightened it down fully with the torque wrench. And I just looked up what the M16 torque value was, and I torqued it up to that. And then after that, I double checked that this was still running dead perpendicular to this surface, this way and this way, and then I was able to put the actual spindle head on. The moving plate down here is a 75 by 75 by 6 box section, and then on top of that I've welded a 20 by 50 flat bar on top of that. On the side here I've welded on some angle irons. So these ones were angle irons that I've cut to form a sort of an angle or a piece this way. And then this is also an angle iron here, which attaches to the 20mm plates on the bottom, which are then bolted to the carriages. The top plate here, I don't know whether I've shown it yet, but I had a wee problem with the spindle, and the toolwork came out of the machine as I was going through and surfacing this. So basically the top here, this is also a bit of boilerplate. It was 50mm thick, so I'll be machining it down. It'll probably be about 45 by the time I'm finished with it, and I'm going to trim the sides up with the end mill as well, just to make it a bit nicer looking. I like using scrap steel because it's free. That's a consideration that you need to make as well if you're going to be building a machine yourself. What material are you going to use? What are you wanting to cut? So if you're wanting to cut wood, aluminium, plastics, things like that, your aluminium extrusion frame probably going to be fine. Personally, if I was going to make a router or anything like that that is actually going to see proper loads, I would avoid making it out of wood or aluminium, and I would stick to a steel construction. You don't necessarily have to know how to weld. You could bolt the table together. For a machine that's going to actually be cutting something, I would prefer to use steel so that I know that it's rigid and strong and shouldn't deflect as much with cutting loads. So I guess the next thing I should talk about is the linear motion system. So basically on this machine I've used the Harwin 25mm linear rails. I've used that on the X, Y and the Z axes, and then I'm using ball screws as well for my motion system. The reason I went with these particular rails as opposed to say like this kind of a rail where it's a round bar and it's got a sort of a mounting plate, and then it's got these. If you look at how much movement you can get on that, that was too much for my liking. For this machine, cutting steel needs to be super rigid, and yeah, I didn't want to skimp out on, you know, getting a cheaper rail and then having a machine that didn't do what I wanted it to do. When you're considering your machine's linear motion system, there are these options. Maybe for like a wood router or something like that, something like this would probably be just fine. But if you're wanting to cut steel and harder things, I'd probably recommend these rails here. For the likes of, say, if you want to keep it cheap and you're just building a laser or maybe a plasma cutter or a 3D printer, something that's not going to see any loads at all, just a simple round bar with the ball bearing. I guess the next thing is the actual drive of the linear system. So we've got the rails and then we've got the ball screw. So the ball screw is what actually converts the rotational movement of the servo or stepper motor into linear motion of the machine. So on this machine, I have used 20mm ball screws for the X and the Y axes, and then this is a 16mm ball screw on the Z axis. Got to have these movable couplers. So these couplers allow, when it's spinning, if there's any misalignment, which there will be because obviously I've welded this, so it could pull in, pull out. So this misalignment coupler, I believe these are called Lovejoy couplers. Basically the ball screw and the servo motor, as they're going around, to move kind of like this. So it's still transmitting rotational power, but it can move like this. Now, the motors that I've chosen for this machine, these are a 1 horsepower servo motor. When we go around the back of the cabinet, I'll show you the drives and things like that. But basically, in the back of here, there's an encoder. And then this, in the back of this, the encoder is a 10,000 line encoder. So for every 360 degrees of rotation that this shaft does, this is giving 10,000 pulses as it goes around for one 360 degree rotation. So pretty precise, which means that the drivers are constantly monitoring each of the servo motors, which means that when the machine crashed here, it actually cut the whole machine off and stopped. So the motor stalled, it alarmed out the system, and then that turned it to an e-stop essentially. I really like the closed loop system, which is with encoders. You can get closed loop stepper motors. When I was looking at these, they were roughly the same price, and these are so much quieter than what a stepper motor is. If you've ever seen 3D printers and things like that, or things with stepper motors, they're quite noisy. But this, I'll just show you sort of how quiet these are. Yeah, so you can see these are rather quiet motors. That's really what I wanted for this machine. Just because of the fact that, you know, the stepper motors make a lot of noise. I wanted the servos also for speed. So the speed of the servo is about 3,000 RPM, and then these are a 5mm pitch. So for every 360 degrees, this will move 5mm. So basically every 5mm of movement, there's 10,000 lines on this encoder being read. So you can imagine chopping up 5mm into 10,000 different spacings as the resolution that I can get on this machine. The servo motors, I think roughly New Zealand, they were about $500 a piece. So there's about $1,500 worth of servo motors in this. The rails and things, not very expensive. I've probably got, this is all from memory, probably about $80 per ball screw, and then probably another 110 maybe per linear rail. For the price of them, they're pretty cheap, really. And especially when you look at the size of this machine and what I've built, compared to, say, a commercial machine. Obviously, this is going to be nowhere near as good as a commercial machine because it's not a cast iron body. All my surfaces aren't perfectly machined like theirs. But for what I've built here, this will be plenty good enough for what I do in my workshop. So yeah, that's sort of why I went with the servo motor, just for the resolution, the speed, and the power of it. Being a 1 horsepower, it's, yeah, you can't stop them. So another feature that I've added to this machine is I've also done an automatic oiling system. So my automatic oiling system uses some special valves. And these special valves, basically, there's 5 outputs, and then there's an input and another output out the side, which is just straight through. So you can link, say, the one on my x-axis to my one on my y-axis, and then back out and then to the controller. So basically what these metering valves do is they meter out a perfect amount of oil for each of the carriage blocks and the ball screw. It's a bit of a wizardry science, but from what I understand, in each of the metering blocks there's a pin, and as the oil pressure goes up, the pin comes out, which then stores that oil inside the metering unit itself. And then basically when I turn the power off to the pump, that flow stops. There's no more pressure. Once the pressure goes away, those pins then push all of that oil out into the linear guide rails and the ball screw. So that should keep everything well lubricated. And spindle wise, I've gone with a BT30 spindle. So this is an automatic tool change BT30 spindle off of AliExpress. I've had a few issues with it. One of the issues was up in here, there's a Allen key, and that basically came a bit loose, which meant the tool was rattling around in there a bit. That happened after this happened, so I don't know whether that was a combination of the two things. The whole reason why this happened was because in the top of the spindle, where the air ram pushes down onto the top of the automatic tool change to push the claw out, and just to show you, this is what I use for my tool holders. So this is a BT30 taper, 30mm here, and then it's tapered. So the claw comes out, you put the tool in, it grabs it and pulls it up into the top of the spindle there. Now, what happened was there's a little Allen key, a little grub screw right at the top of that spindle. And basically what happened was the grub screw rattled itself loose and unwound, and then it welded itself to the shaft of my ram here, which then, because obviously it's being a thread and this is spinning this way, meant that because they were welded, it basically was winding itself down that thread, which then pushed the tool changer out and then made the tool embed itself into here. And luckily I had the closed loop servos and it shut the whole machine off. So if you're going to be buying one of these from AliExpress, I would recommend them. They are really good. They turn really nice. They're really tight. But yeah, that I would definitely pull that out and Loctite it in. I believe the reason for it being in there is because you can actually run through spindle coolant on this, because when I pulled it out, you could actually see right through. So it's an MPT thread, the grub screw, so that kind of indicated to me that it was for through spindle coolant. On the top of the machine here, this is a 3 horsepower AC motor. Find them on, you know, machines, air compressors, 3-phase tools, things like that. So I actually scored this off of Facebook for about $40. The max RPM on this is 3,000 RPM, so the spindle bearings in this can take 6,000 RPM. So I'm only really running it at half the speed that it can, but for the spindle motor upgrade, that's going to be another probably 1,800 New Zealand dollars. So it is on the cards, but just not quite yet. The way this is controlled is through a VFD, and the VFD or variable frequency drive, basically what that does is it takes a 0 to 10 volt signal from my CNC for PC C82 CNC control board, and it takes that 0 to 10 volt signal, and then it basically does a linear path. So 0 volts being 0 RPM, 10 volts being 3,000 RPM. And then basically the software will just send it the signal depending on what spindle speed I've set up in my CAD software. So the CAD software I'm using to run this machine is Fusion 360. I bought a license, so I've got the full tool change and everything. So once I build the tool changer for the side of this machine, I will be able to, I'll be able to go through and basically set up an entire program on the machine and then have the machine cut the whole entire program for me without me having to press the button, put the tool in and do all of that. I also have a touch probe, a 3D touch probe and a tool setter on their way from CNC for PC. They've been very helpful. I've had a few dumb questions that I've asked and there's been no issue with them answering them for me. So yeah, the customer service is great, and there's actually in the link in the description if you want to pick up the C82 board that I'm running on this machine. It is an affiliate link, so I get a wee commission off of that if you purchase the product, but it doesn't cost you anymore, and it just helps out the channel and helps me build more projects like this. So what else have we got? I've got on my X, Y, and Z, I've got my limit switches. So basically what I can do is I can press home, reference all home, and it should bring the Z up to the top, and then of course X doesn't want to move. Right, so we'll try that again. So if we reference all home, the Z-axis will reference itself first. So that's Z0 set for machine coordinates. Then my X-axis will move to its limit switch, which that sets X home, or X0, and then the Y comes in, and that's Y0. So now the machine is completely homed, XYZ 0 for machine coordinates, and then basically when you go through, you'll have your tool in or your probe in, you'll come and probe your parts, and then that'll be your work coordinates. So machine and work coordinates are a bit different, but we'll talk about that in other videos. So yeah, I think that's most of what I want to talk about at the front of the machine here. I think what we'll do now is I'll take you around the back of the machine and we'll go and have a look at the computer and the control system and how I'm actually controlling this machine. And then I'll give you some final thoughts and yeah, we'll go from there. So I'll start off here sort of at the top of my cabinet. So this is my basically control cabinet. So I've housed all of the servo drives, all the power, and then all the computer and all the rest of it down the bottom. So basically what I've done is I've set this up as basically a switchboard. So I can turn the power off to the PC, X, Y, and Z servo drives, and then my 24 volt power supply, which runs the actual computer. This here is the main switch. And then this switch here is to turn on the VFD. The VFD is a 3-phase switch. So basically I've got 3-phase power coming in here, and then I've looped off 3-phase over to here. And then out of here, each phase this is one phase, this is one phase, and this is one phase. The reason you want to, if you've got 3-phase, is spread the phase, spread all the power over the phases. So I've basically got one stepper, one servo drive running off of each phase. And then I've got the computer running off of this phase, and then I've got the 24-volt power supply running off of this phase. So that just keeps everything sort of balanced, and that means you're not drawing too much power from one or the other phase. So that's the switchboard part. So that's my AC power coming in. If you come down here, I've got my X, Y, and my Z servo motors. So these servo motors, as the machine's moving, they display the RPM of the servo motor. They'll also connect, this is the encoder input. So those encoders that I was talking about on that servo motor before, basically that's coming in here, and then this is doing all the calculations and keeping an eye on where it is and making sure that where the CNC controller told it to go is where the servo motor has gone, or it has turned that many revolutions. So basically these are a single phase unit. So again, each phase comes to each one. This is where the wiring goes. So this is the input power. So the input power here comes from here in, and then this is the output power. So those motors are AC servo motors as well. So basically these are like a VFD, but they've got an encoder input on them as well. So this is your 3-phase output wires to the servo motor, and these are your grounds. Obviously you don't want to be touching those wires. There will be a front put on here and everything, but I've just been testing the machine, so I haven't quite got to that point yet. I've tried to run everything through these cable holders. I've got all the covers and things, so everything should look nice and tidy once it's all finished. What I've also tried to do with this is keep all of my AC power over one side and up the top, and then keep all of my DC power and sensors and things coming in on the other side and down the bottom. The reason for this is you don't want to get too much interference between the AC and the DC and the sensors, because the AC power doing the AC waveform will actually interfere with the sensors and can sometimes screw up your machining if you get some interference, so you don't want that to happen. Most of the wires I've tried to do is shielded wires, and then these are all Cat 6 wires. So all of the servo drives are running off of Ethernet, and then these boards here basically just convert the output pins to Ethernet so that my controller board, the C82 control board, can talk to these. So if we come down here, basically what we've got going on here is, down here I've got basically just your standard computer. This standard computer is running Windows 10, and I'm running Mark IV, my control software. There are other options for control software. You can use Linux CNC. There's like the Masso and the Centroid Acorn kit. In my opinion, they were a bit pricey for my liking for what they did. And after talking to Arturo down at CNC for PC, he sort of, we ran through a whole bunch of things. We ran through what I was wanting to do with the machine, the servo or the motors that I was using, my power requirements, things like that. And basically we came up with the C82 board. So this is running an Ethernet smooth stepper, and then this is basically a breakout board that plugs into that, and then these are my outputs and inputs, so X, Y, Z, A, B, C. So I can run basically a 5-axis and the spindle, or I can run 4-axis, then the automatic tool changer mechanism, and I think number 6 is actually my spindle control. And then down here you've got inputs and outputs, so you can connect whatever you like up to that. Up here I've got my outputs connected through, and they connect to these relays. So this relay here is on, which is basically the relay to keep the air ram up so that it's not rubbing on the tool. And then when you press that tool change button, it turns this one off, and then it'll turn this one on, which will push that ram down, and then that'll go and allow you to do the tool change. This board here runs off of this 24-volt power supply. This power supply was also supplied by CNC for PC, and it all came with DIN rail mounts and things like that, so that kept it nice and simple. So yeah, it's definitely the way to go, is DIN rail mounts if you can get a control board like that. I guess considerations for control boards, again, what are you wanting to do with it? So if you're just building a basic router, you don't really need, you know, sensors and inputs and bits and pieces like that. You can just have, say, 3 inputs for your limit switches or whatever, or you could even do all 3 your limit switches off of 1 input if you wanted. If you talk to the guys down at CNC for PC, they'll be able to sort you out, help you out with whatever you need, and recommend what kind of board you'd want to use. If you do have any questions though, leave them down in the comments, and I can make another video on it. Right, so we just made those cuts in steel. So I've got some 608 RS bearings, and these are basically the same bearing in the 608. Just your standard skateboard bearing. So try this one. Probably a little bit loose, there's a bit of play there, but that was 0.02 I think. That one there, that's basically a perfect fit, so that's interesting. Whether these ones are more accurate than these ones, I don't know, but the inner board's definitely different. So, and then the outer fit on that, well, I reckon I would knock that in there pretty well. That's super close. I think I modeled that at 22.01, so it's only got 0.01 of a mil of clearance, but like if I had a tiny bit more, that would definitely go. But yeah, it's making beautiful circles anyway, so that's good. There's no issue with clearance in that, so that's